Hello and welcome. My name is Farnel Hieber. I'm Smart Charging Coach at Vector, and I want to show you today how you can analyze your smart charging communication if the communication is TLS encrypted. So last year we saw new cars and new charging stations that support plug and charge with TLS. So this topic gets more and more important, and we want to show you our solution for this challenge in Canoe. So first of all, I want to give a short introduction into smart charging and TLS. So TLS is used for plug and charge and value-added services if you use ISO 15118-2. And if you use the next document, the ISO 15118-20, TLS will be always mandatory. So for plug and charge and AM. Both documents use TLS 1.2 and the following Cipher suites. And TLS is not only used to protect the confidentiality of the transmitted data, it also ensures the integrity and authenticate the EVC. So what is the motivation to decrypt the TLS trace? First of all, we see two different use cases. One use case is you test against real EVSEs. Another use case is you test against an EVSE simulation, like our Canoe EVSE simulation. And in this use case, for example, a software in the loop setup with our VAO virtual target, which simulates an ECU. You run your simulated ECU against our EVSE simulation, which has included also a TLS server. And this TLS server has its master secret, so this communication can be automatically decrypted. That's why we recommend to use as long as possible the EVSE simulation. This is also possible if you have your first A and B sample and together with our VT system, and as well if you have your first cars. But you probably want to test also your cars against real EVSE to check if they are interoperable. So how does this setup looks like? So here we have our charging station and our electric vehicle, and we listen to this communication with our CCS listener. The CCS listener is connected to the cable via the inductive coupler. It's also possible to connect the CCS listener directly to the control pilot. So this ensures that you can listen to the communication passively. So that's not a man-in-the-middle setup. So you do not influence the communication between the charging station and the electric vehicle. That's why you can identify issues in the timings or issues in the messages. But now the big question is, if this communication is TLS encrypted, how can you decrypt this TLS communication? So I will show you now 4 solutions that Canoe supports. First of all, you can use Null Cipher suite. So both sides, the electric vehicle and the charging station, has to support the Null Cipher suite, and they have to agree to it in the TLS handshake. Another solution is if one side, the charging station or the electric vehicle, provide a master secret, you can manually type this master secret into the Vector Security Manager. The Vector Security Manager is a tool which comes with your Canoe installation. Another possibility is you can set the master secret via couple code in the Vector Security Manager, or you can transmit the master secret via UDP frame. So Canoe will listen to this UDP frame and decrypt your trace automatically. So I want to show you now the 4 solutions. How do they look like and how can you configure the solutions in Canoe. So first of all, how to use the Null Cipher suite. As I said already, both sides has to be provide the Null Cipher support, so the electric vehicle and the charging stations. So they will agree to this Null Cipher suite in the TLS handshake, and you will see the messages here. So you support uproot call and session setup. So this is already supported since GNU 13 Service Pack 2. So maybe some of you already use this feature. The next solution is you can set the master secret in the Vector Security Manager. You can open the Vector Security Manager, you click on the TLS Observer profile, add parameters, you choose here master secret, and a new window will appear where you can type in your master secret and your client random. The client random is used to identify the TLS session in your trace. So you can have multiple TLS sessions in your trace, and GNU will know the correct session according to the TLS, to the client random. Next solution is you can set a master secret via couple code. You have a very generic way to set the master secret. So you can, for example, receive the master secret via diagnostic or CAN message and set the master secret dynamically in your couple code. So you just have to set the master secret to this system variable TLS master secret. Another possibility is you can set the master secret via UDP frame. So the trace looks like this here. During the TLS handshake, one side, the electric vehicle or the charging stations, has to send the UDP frame with the master secret, and the master secret has to be the format in NNS keylog format. Looks like this here, for example. So label with the value client random. This is separated by the value of the client random with a space, and the client random and the master secret are also separated by a space. How can you configure now GNU that GNU will automatically decrypt the trace? You click to the TLS Observer profile, click Add Parameters, you choose Master Secret Source. This new window will here appear, and you can configure the source IP, source port, destination IP, and destination port of the UDP frame. So if GNU sees a UDP frame with these values in the trace, GNU will automatically search for the master secret, extract the master secret, and decrypt the trace. So we can offer you also another solution. If GNU is your simulation endpoint, that you can store the master secret in the log file. So how does this setup looks like? Here, for example, you have our giant conformance test system, which used GNU to simulate the EBSE, and we run here our conformance test, for example, also plug and charge conformance test with TLS. So if you do a test case and you want to save this log file to show it a colleague, for example, you can save this log file with the master secret that your colleague is able to see the unencrypted messages. So the condition is that GNU is TLS client or TLS server. In this case, it's TLS server. And we support the following files: ASCII, BLF, and MF4. So this is the setup. You have your GNU simulation for the charging station with the TLS server. We store the master secret in the log file, and this is done by setting the system variable TLS master secret. So that ensures that you can analyze the trace also in offline mode. We come to our conclusion. So what solutions do we offer that you can analyze a TLS encrypted communication? First of all, the Null Cipher. So both sides have to agree to the Null Cipher suite, so the electric vehicle and the charging station, and the messages will be transmitted unencrypted. Another possibility is that you can set the master secret manually in the Vector Security Manager. So both solutions are already available since GNU 13 Service Pack 2. Another solution is you can set the master secret via couple code or via a UDP frame. So Canoe will listen to this UDP frame, extract the master secret, and decrypt the trace. Or you can set the master secret in a log file. So the solutions are available since Canoe 14. The release of Canoe 14 was last year, so maybe some of you use already some of these solutions. Last but not least, the solutions are independent of the smart charging communication. That means that you can use these solutions also for other protocols like DoIP, SumIP, MQTT, which is an IoT protocol, or HTTPS. But please keep in mind, if you provide a master secret or you enable the Null Cipher suite, you have to deactivate these features in the serial production. So thank you very much for your time. I hope you see lots more electric vehicle and charging stations that support plug and charge in the future. Bye-bye.